Yeah.
Yeah. I can count on you then, right?
Yeah.
Okay.
But I'm just worried about maybe I just forget something, maybe a little bit. I cannot remember what I learned before.
Oh, sorry. Oh, okay.
Yeah, I can remember offhand.
Yeah. All right. That's awesome.
I need to have a review. I think so. Yeah.
Oh, I do?
Yeah.
Yeah. Like,
Just next.
oh, where were you? Okay.
I don't know. Maybe I just. The average grade is about 84.
Just take it and run. I don't think you're but I want the factor. Oh, Jimmy. Oh, this is a problem set. Oh, Jimmy, this is a problem set. I told you I didn't want back ever. This is the one I decided to abandon.
Yeah, it's a problem.
I don't like how I watch that. And I think they started being honest about it. I won. Two things.
Did you get drunk at the beach?
Not a good pick for this. Don't worry, it's a problem. We're okay. I was like, don't make sure back. Oh, no, the midterms, they're up there. They're up there. So you can't tell. Yeah, amazing. Different colored negative space. Yeah. Just look at the negative space. Oh, we forgot that I have one. I've got the playground. I really love them. No, yeah, but I don't. Is this your binder?
Yeah.
Okay, I just want to make sure you don't forget it.
Okay.
I'm kind of covering it, sorry. It's great. So I don't agree that this is not a court mail with possible for that. And we're like, however, I will be back next week. This is a great.
It's a fundraiser.
Yeah. It is a fundraiser.
Oh yeah.
So you, this is like raw. Yeah.
Yeah.
You got the thoughts? Oh, for real? That's why I'm struggling right now. And then I followed it by.
Yeah, we're going to talk about having
and then they do like different rounds. They do this but they like just for each round, they'll do like money, everything. Several like three. Oh. Like our game and might get like a painful or might get like anything. Oh yeah. You're excited? Yeah. And that that's
Oh. They're kind of rules for it. Why was it nice? Probably said something about it.
I had like some for like 3 years already. My teacher would do one well. And this time I did not get any free
Mine was kind of blue background.
I know I have a picture of that, but because I sent it to you and then like it was like 6 chicken breasts. Like just like oh my! I tried to get it right, like a massive thing, but he was like. No. I will take it if he's like, I want it. Every Sunday. Yeah, so they're on the street, but how do you go? Right? Very fun. Yeah, you're good. And then we were like, my friend left to go to yoga. It was my fault. Yeah. Oh no, I don't want this. Which one is this? Okay. Ever love her.
Wiz.
How could I blow it?
Wiz.
Oh.
Yeah, I was just wondering, did we talk about this?
Yeah.
My friend, I think it's like, learn how to do it, learn how to do it after I just don't remember like this name.
Yeah.
Well, I'm just like.
No, you use it. No, oh, so the music.
Oh.
Ready?
Yeah. I just don't know, I thought you just got eyeballs or something.
Oh.
Yeah, no, I got
Oh, that's okay.
Oh, no.
Oh,
Sorry, thank you.
I'm your competition.
I saw it was
Oh.
That's awesome. Okay. Did you? Okay. Yeah. Okay. I have a question.
Oh.
男生多少呢？男生就找老师
Oh.
I didn't know that you were collecting them.
Oh, yeah.
I'm also useless, but I can go back to it. Okay.
I'm sorry.
That's okay.
要我让你找。
Is there anyone who didn't get the midterm or the problem setback or all good? Okay. Okay. Yeah. Um,
你要去找老师。低于6我要去找老师。
I'm sorry. I'll just keep looking.
Do you know if he also and he's talking
Yeah, let's start. So today I'm gonna make some announcements and review the midterm one really briefly, and then I'll preview the next lecture. Because the next 2 lectures contain a lot of information. So I would rather preview the next lecture. Yeah. So the midterm, the grade, the mean and median are both about 84%. Please let me know if you have any questions. And we have a co-winners of this cheat sheet contest, and it's Frankie and Courtney. So. Let me know what you would like to have after. But congrats. Yeah. Frankie draw a lot of cats, cat stickers, and Courtney draw a unicorn. So that was what I appreciated. Anyways, please let me know if you have any questions about end of midterm questions, and then I'm really open to discussing this partial credits and stuff like that, because I know you care about the grades because you have to class. I do understand that, so just let me know if you have any questions about anything. So I don't mind any partial credits related questions. And yeah.
What's the meaning of 84?
84%. Oh no. Percent. If you change your grade, it's percentage.
Oh.
Yeah. Yeah. I don't. The curve will be decided after. I mean, there is no a threshold for A's or B's that were pre-decided in the first place. So I think judged by like average, or the like basic understanding of materials, based off of that, like subjective judgment, how we. So the grade works by me recommending the grade level to decide on it after by adjusting. And yeah, so let's talk about oops. Some questions. The first one I would like to talk about is short answers 1.2, which says a researcher is analyzing a very large sample. The researcher is happy because bias decreases and sample size increases. Do you agree with the researcher? Why not? I would not agree with the researcher because it is a bias decreases as sample size increases only for a consistent estimator, right? So as long as you're using a consistent estimator, it is true. But if the question does not specify whether you are using a consistent estimator, right? For example, we came up with this weird estimator OLS prime, where this is exactly the same as OLS, except we are just adding 3 for whatever reason. Okay? And even though beta is right here, as you increase your sample size, it'll be closer and closer to beta plus 3. Or does that make sense? So it's not a consistent estimator in this case. In that case, if you increase the sample size, bias won't necessarily be decreasing. Does that make sense? Bias will still be 3. Good. So bias is nothing to do with sample size per se. Does that make sense? All right, awesome. Yeah, let's move on to 1.7. A student claims that she does not like forcing exact matching because too often, blah, blah, blah. So I would tell her that she is, so forcing exact matching can drop a lot of observations when this is more like exact matching per se, exact matching, but it applies to course and exact matching. And so treatment group, control group, there's 100 people, 100 people, 100 people, 0 person. Okay, so there is no women in the control group. In that case, to achieve the comparability, you are dropping women from the sample in this matching situation, right? So in that sense, she can be right. She is right. Because it can drop a lot of observations because precisely for the causal matching. Right? But then I would comment that and she is also correct that it leads to the causal effect only for men in that case. But then I would comment that, is that a good reason to not like a certain method? Sure, your causal effect is only applicable to men, which means that you are losing some sort of generalized filter. But then you are strengthening your causal causality. So there is always a trade-off between the two. Does that make sense? So it is correct that she is correct in that statement per se, but I would comment on that statement that still you're losing some sort of generalizability, but you are having a stronger causality. So there is always a trade-off. So I think I was generous with the grading of this question because there were a lot of different answers. But let me know if you have any questions or asking for partial credits. You should definitely do that. All right. Any questions about 1.7? No. Yeah.
So what is the correct way to lose the generalizability?
So in that case, the causal effect is only applicable for men, right? You're losing generalizability. You're not applying the causal effect for women. You cannot do that, right? Does that make sense? Yeah. So that's why. But you're increasing your confidence in causality. Let's move on to the next question. 1.8. A student argues that the EOS regression assumption that X transpose E is 0 is rather redundant because from his experiences, the linear correlation between the standardized and variables in the estimated error curve was exactly 0 in regression from the regression model. This student is not right because the student is referring to first. What the student is referring to is X transpose E hat being 0. This is different from X transpose E being 0. So what it means is that basically the estimated error terms are estimated based estimation of the error terms is predicated on the assumption that X transpose E is 0. So it should be always 0 by construction. It is built in. This E hat is designed in that way. And one of the core Wallace assumptions is X transpose E is 0. It can be most certainly violated by omitted variable biases. So for example, if there is unobserved confounders, it can be violated. That assumption is violated. So that way, that assumption is not redundant. Any questions? Nope. All right. Any questions about the midterm in general, or? Nope. All right. Okay. Let's move on then. So we're gonna preview the next lecture. So the next lecture will be about the violation of IID assumptions and robust standard errors and generalized least squares model or estimation. Okay. So far we have assumed that EI will follow a normal distribution of 0, the mean of 0, and the standard deviation of sigma with the IID assumption, which means that error term is independent and identically distributed. Good. There is certain violation patterns of violations. The first one is heteroskedasticity. Okay, where error term looks like that. The pattern of error term looks like this. So variance of error term is different across the levels of X variables. A good example is the relationship between income and housing expenditure. Let's say we are analyzing housing expenditure as the outcome here. And you are running the regression of that variable on income annually. Okay. So in that case, errors are most likely have that heteroskedastic patterns. Why is that? The errors will look like that, most likely. Anyone? X variable is income. So in that case, if you have lower income, you don't have much choices in housing expenditures. So that's why the variance of error terms is really small. But as you have higher incomes, you can either have you can spend lower money on housing, or you can spend a lot of money on housing as well. So that's why variance of the error term gets larger as income increases. Does that make sense? Yep, awesome. And another pattern of violation of ideal-related errors. So let's say we are analyzing students' SAT scores. SAT scores are the outcome. And you are running the regression of the outcome on parental income. Good. In that case, but these markers represent school A students, and these blank markers represent school B students. Good. All right. So even after running the regression of SAT score on parental income, there has been some patterns, meaning that the school A students share some sort of characteristics, and that way they have higher scores in SAT in general. Whereas school B's students have lower scores in general, even even on your regression line. Very cool. Does that make sense? So it means that by looking at the level of errors, which is positive here, you can expect what kind of direction the error will be for another student from school A. Good. So since this is positive, you're guessing that, oh, this is most likely be positive. This means correlated errors. Good. Yeah.
So by looking at the error terms, you can tell which student wants to school.
Oh, so you have to have the information of the school first, and then basically look at error pairs by each school and try to figure out, oh, this seems like correlated. I will mention that, but the error terms are all theoretical terms. I'll mention that. All right, good. So we're learning new concept of this is covariance matrix of error terms. This is noted as variance of E1, covariance of E1 and E2, E1 and En, variance of E2, variance of En, covariance, E2, E1, covariance of En, E1. So this is N by N matrix, where N represents the sample size. So there are N individuals in the sample, and they have each error term has variances. And then there are covariances going on among these error terms. Okay. But what does it mean by variance of errors and covariance of errors? They're supposed to be, isn't that supposed to be 0 now that errors are estimated? Why there is variances going on in the error terms? It's just one number. It could be. Except that it's not a number. E1 is not a number. E1 is a random variable because it is not E1 hat. This is not the estimated error. This is a theoretical error if you sample multiple times. So E1 hat is an estimated error when you calculate with your one-shot sample. This is different from E1. Your theoretical distribution or your theoretical errors. Does that make sense? Good. So I'll clarify what I mean by that. E1, E2, etc., En. Sample 1 sample 2, sample in M, yeah. And then let's say we have yi 2 plus 3 xi ei. So that's the estimated regression line, right? Good. And then if you, this is the real regression line here. So in sample 1, yi could be, say, 14. You would draw a sample, it happened to be the first observations, yi happens to be 14. Good. And it happens to be 10 for the second sample. If you draw a sample again, the first observation has 10 as y variable. It's all theoretical, right? You have one-shot sample in reality. But it's all theoretical situation going on right here. And it can be 8, for example. Good. And you are calculating your error by plugging in all the numbers. 2 plus 3, let's say x1 is 4. That way, you can calculate E1 in your specific sample 1, right? So that becomes E1 hat for sample 1. Does that make sense? All good so far? And then, in the sample 2, you are subtracting the same number. In this case, xi happen to be are assumed to be same across all samples, and etc. etc. So note that x's are all same within E1. Okay? That's what it means by x's being non-stochastic assumption. Good. So you have all the E1 hats, right? And then you are drawing a distribution out of it. So that's the distribution for E1. Again, E1 is a different concept from E1 hat. This kind of reminds you of the midterm question 1.8, right? Actually, I made this question too, because this is really important. Yeah. If you found it hard, I'm sorry, but yeah, I think it's a good, really reminder of like what's going on here.
So where is E1 hat?
So each one is E1 hat. And then if you draw a distribution out of it, and then this becomes E1's. E1's distribution. Yeah. Yeah, anyways.
What about 4? Value.
Oh, what?
The value 4.
4?
Yeah.
4 is assumed to, so x1 is assumed to be 4 for all samples.
So that should be 2 plus 3 times.
For all samples. For all samples.
Yeah.
Yeah. So that's what it means by x being non-stochastic.
2 plus 3 times 4.
Oh, yeah, yeah. Good. And then you have 9, 2 plus 3, say 5, and 10, 2 plus 3 multiplied by 5, 16, 2 plus multiplied by 5, etc. And then you would have distribution for each one error.
So the difference between 14 and 2 plus 3 times 4 is the E1 hat.
Oh, what?
What's so the value we got?
This one?
The upper one.
This one?
The middle.
This
Yeah.
one?
Yeah, is that E1 hat after we got?
Yeah, E1 hat. That's E1 hat for that sample. And that's E1 hat for this sample. etc. This is all theoretical. In real research, you have only one shot sample. Good?
Can I say?
Yeah.
Those sample distribution is a
It's not sampling distribution. No. It's not a sample distribution. It's just sample distribution of error. Distribution of errors.
sample distribution of E1.
No, just the distribution of E1.
Just distribution.
Theoretical distribution. Good. Any questions?
So should we change the notation EI to EI hats? The
So, here,
upper Y equals 2 plus 3 times XI plus I.
what?
Should I change the notation EI?
This one?
Yeah.
No,
EI
this
hats.
is, so basically, if you have, so not necessarily, so it really depends on the situation you're talking about. So let's say you have all estimated the beta coefficients, and then you got the estimated errors, then you would have this one, right?
Yeah.
Okay. So, but then if you are thinking about a regression with OLS estimation, before getting the estimated errors, then it becomes this one. Yeah, it's a tricky one actually. So it really depends on what you mean by the situation you're talking about. It's a tricky one. Yeah. If you have any questions, I'm happy to answer the questions after the session. Good. Any questions? Nope. All right. So that's why errors can have variances and covariances. Good. Because E1 or each EI is a random variable. It's not a number. E1 hat or EI hat is a number, but EI is a random variable. Good. It can vary depending on which sample you draw. Good. This is really important, actually, for your future endeavor of quantitative research or reading textbooks or articles about explaining certain methods and stuff like that, because if you don't really get what's going on with the error structure, it gets really difficult. So it's really important for your future endeavor, I would say.
So the 1 year is like an observation, first observation, like a drawing the data set.
A what?
Like 1 year is like a
One.
observation 1.
This one.
Yeah. What's the 1?
E1.
Yeah.
Yeah, E1 is the first observations error term within not within specific sample.
So how hotline link to the real data set in like data is the first row of the observation, first person.
Yeah, first row of the first person, but it can vary depending on the sample. Good. Yeah. And yeah. All right. Good. Let's cover covariance matrix and violations of IID structure. So heteroskedasticity is formally noted as variance of EI being different from variance of EJ when I and J are different and correlated errors covariance between I and J not being 0 when I and J are different. I think it can be confusing, so I'll explain it with examples. So let's say we have 3 samples. So a sample that consists of 3 individuals or units. In that case, variance of E1, variance of E2, variance of E3 are all 2s. So that's why it is homoskedasticity going on. Good. And errors are not correlated. So that's this is uncorrelated error structures. So E1 and E2 have 0 covariance, meaning that they're not really correlated with each other. By looking at E1, you cannot really predict what the value of E2 would be. Good. And but in this case, this is heteroskedastic and uncorrelated. Because each error term are different and they're not correlated with each other because they're all 0s. Two. This is homoskedasticity, but correlated. Because variance of each error term is the same, but there is covariance between E1 and E3 here, right? And this matrix is symmetrical because covariance between E1 and E3 is same as covariance between E3 and E1. Good. And lastly, the error structures are both heteroskedastic and correlated. Good. Any questions? Was it too fast or good amount of speed or? Good. All right. Good. And let's talk about consequences of heteroscedasticity or correlated errors. It will be discussed in the next lecture, but the gist of it is basically beta coefficient. It is pretty much nothing to do with beta estimator per se, the slope per se. The beta estimator is still unbiased and consistent, but it's just that it is not efficient. So to achieve the same level of standard error, you need more sample size. It means more money and time to gather more sample size. Right? But the standard error of the beta coefficient is biased. So that way, the significance test will be incorrect, even though the beta coefficient is not biased. Does that make sense so far, or? Good. So the beta coefficient still unbiased and consistent, but the standard errors are biased. That's the key takeaway. I won't explain too much about the mechanics behind it because it will be discussed in the lecture, but yeah, that's the gist of it. All right, then there are some solutions of heteroscedastic or correlated errors. The first one is to respecify the regression model to achieve the full independence between X and E. Right? So I'll explain what I mean in the Stata example. So I won't say too much about it in detail, but it's basically controlling some variables to counter the pattern of heteroscedasticity with the opposite pattern of heteroscedasticity. I'll explain that in more detail with the Stata in the Stata example. And then the second option is OLS estimation with robust standard errors. So, have you guys covered robust standard errors in 361? Yeah? Okay, good. Yeah. So this procedure uses residuals from OLS to estimate certain error structure. And you do not need to know the mechanics for this class. But what you have to know is that you don't need to know the source of heteroscedasticity to use robust standard error. Right. So in the example of income and housing expenditure, you suspected that there is some certain mechanisms going on with the income, right? But with the use of robust standard errors, you don't really need to know the mechanics behind the mechanism behind heteroscedasticity. That's the strength of robust standard error. It merely corrects, estimates some sort of error structures, and then corrects the standard error. That's it. Good. So basically, there were some incorrect things going on with the standard errors, right? It's just merely incorrect. That's it. It solves the problem of bias in the standard errors, but not the problem of efficiency of the OLS beta estimator. means that theoretically there could be other estimators that could yield lower standard errors with the same sample size. So it costs a lot of money to use if you decide to use robust standard error, or you're using the money inefficiently with the robust standard. Okay. Any questions so far? Yep. And there is some standard error options, robust standard error options. If you think that the errors are heteroscedastic but not really uncorrelated, then you can use Eicher-Huber-White sandwich standard error. And if you think that errors are also correlated, then you can use Liang-Zager standard error. Again, you don't need to know the mechanics. What you have to know is when to use what, and what is the strength and limitation. Just in a way, it can be a memorization, but you have the cheat sheet, so you don't really have to memorize, quote unquote, memorize. FYI, robust standard errors are not necessarily larger than simple standard errors, because in the school's examples, so we assume that there is high positive correlations among errors within the specific clusters or schools, right? In terms of when you're running the regression of SAT scores, right? If you remember that example. Right? But then negative correlation can happen because let's say someone is getting more resources for whatever reason from school, and then that systematically affects other people's achievement negative. If that's the case, errors within the clusters can be negative. Okay. But then, in the whole aggregate sample, these dynamics offset each other, so there is no correlations in the overall. If that's the case, robust standard errors can be larger, can be smaller than simple standard. This is more of an FYI. I think this is not like that will be coming up on the exam. So, but I was just wanted to mention that there could be some negative correlations among errors within clusters, and that could make robust standard errors smaller than simple standard errors. This is actually related to a common conception about robust standard errors. So robust sounds like you're having larger standard errors. So that way you have you lower some key statistic to be more conservative in rejecting the null hypothesis, right? Does that make sense? So if you have larger standard error, key statistic will go down, and you are less likely to reject the null hypothesis. But this is a misconception about robust standard errors, and robust standard errors can be actually smaller than simple standard errors. That's the key takeaway from FYI.
What's the meaning of robust standard error?
Oh, what?
Robust standard error. Like, what does it look like in the equation?
Oh, don't need to know the mechanics. Again, yeah. So we won't cover that in the class. Yeah.
So there's a difference between robust standard error and the traditional standard.
Oh, what?
What's the difference between robust standard error and standard error?
So again, don't need to know the mechanics for this class, but it's just estimating this error structure with the one-shot sample, even though you cannot really exactly know what's going on with the this error structure per se. Right? You're just guessing or estimating this structure based on one-shot sample, and then reflect that in your calculation, in the calculation of standard errors, and that becomes the robust standard error. And the third option is generalized least squares estimation. So here, so the basic intuition behind GLS is that you weight the inverse of the square of the covariance matrix. Square root of the covariance matrix. So I'll explain that. Oh, yeah. Oh, again, don't need to know the mechanics too much. Okay. So for this slide, I won't say much about the mechanics, so I'll just mention the interpretations. So basically, it's weighting individuals. So you're taking certain individuals more seriously in the calculation of regression. So, for example, you're acting as if some people have made themselves into two people. That's what weighting is. You are multiplying some observations. Okay? That's what weighting is. Or for some people, for other people, it'll be like dividing themselves into kind of 1/6 of themselves in the calculation of regressions. This is to achieve efficiency, which was not achieved in robust standard errors. So this is an alternative to robust standard errors because it can be helpful for achieving efficiency. Good. So the purpose of this weighting is that if you weight certain individuals over the others, so that way you can achieve IID errors. So the weights are designed in such a way that you can achieve IID errors. Good. I'll explain more about that in the mechanics part, but this is not required, I would say. And please note that the OLS estimator is not biased in the first place, so GLS beta estimate will be same as OLS. Okay. But then the weight to weight people, you have to know the covariance matrix structure, error covariance matrix structure, or the sigma one, the thing we have seen so far. But then it's all theoretical, right? So there is no way you can get the correct sigma or the error covariance structure with one-shot sigma. Right? So that's why we do not know sigma right here. With one-shot sample, there's no way you can get an error covariance structure. Good. So we either have to assume the covariance structure, which becomes weighted least squares method, estimation method, or empirically estimate the covariance structure, error covariance structure, which becomes feasible generalized squared or generalized least squared method, FGLS. Good. So that's the gist of GLS. GLS is basically weighting some individuals over the others, so that way we can achieve IID errors. But we don't. In the process of weighting individuals, we need to know covariance matrix structure. But it's not really possible with the one-shot sample we have. So you have to either assume it or empirically estimate it. Good. That's the whole story behind GLS. And then there are a couple of ways to diagnose heteroscedastic or correlated errors. Again, there is no way you can correctly know the covariance matrix structure, which means that you cannot correctly know, quote unquote, correctly know if there is a heteroscedasticity going on or correlated error. You can only infer it with your one-shot sample. See what happens, and you can infer it, but not you don't know for sure there is heteroscedasticity or correlated errors. Good. And then the first one is graphical observations, which we'll cover in the state example. So that's fine. And then there are a bunch of formal tests. Okay. And I will cover that in the state example as well. And then there is mechanics part of GLS. I'll cover that. I'll cover more of that in the state example as well. Okay. Any questions so far? So all of the mechanics part we'll cover in the state example. But the basic intuition here is that there could be some violations with IID errors, and then there are multiple ways to infer there is violations, and there are multiple ways to deal with some concerns with the violations. That's the whole story behind it's the next lecture. All right. Don't have any questions. Let's move on to lab exercises. Go to the course website, go to sections, lab exercises, and week 7, and download all of the files. And download all the files and move all the files into your folder and change the directories.
I want all of these. Not all. Yes, there is. See, so no cat folder. Okay, so like, I see. Sorry, I started so hard. All of this.
Any problems or questions with the downloading and stuff?
You know, it could be like yours.
All right. Does anyone need more time or? Yeah, all good? Okay, good. So here, it's basically a practice of the violation of IID assumption. And let's start with this fertility data. The exit command, right below the use command, and execute it. So if you click on the data windows, you will have a bunch of variables, basically. And then, so this data is about fertility data of a little over 4,000 women. And then some observations were dropped because of the missing values and stuff like that. But so it's basically looking at the outcome of CED, or the number of children born to the woman, the number of biological children. And there is predictors include age variable and age at birth, which means age at their first birth, like mother's age at their first birth, and whether the mother used contraception, and the number of children in the household as well. This children variable is not necessarily the number of biological children. They're just cohabiting children in the household. Good. Let's move on to this 1-1-1 graphical observation. Let's say we started with the regression of CEB on age and use MET. Okay. So this is the regression without age after which age at the first birth without that variable. Run the regression, and you have the results, right? This is not necessarily what we're interested in, but age variable is positive and use method is positive as well. And after that, if you run the RBF plot command, then you could see the residuals pattern, right? The estimated is residuals patterns, which is different from the theoretical errors. But what we're trying to do here is to infer the pattern of heteroscedasticity with our one-shot sample. Good. So the y-axis is the estimated residuals, and x-axis is the predicted values of y. or the linear combination of all the x variables, the predicted values. Any questions?
Can we ask question why like data doesn't use
Oh, what?
like ask question like why the code doesn't use
Oh, what? Sorry.
like for example when I run the file, but I already saved it here.
Did you change the directory?
Yeah, you reset it. This is a you
No. Oh, okay.
reset.
Okay. Let's see. Let's see.
This too.
Okay.
Choose this direction to
No, I think it's fine. Yeah, you can just look at it. Honestly. So. All right. So basically, it shows some sort of it suggests some heteroscedasticity, right? Why do you think that is? What's going on here, right? So it seems like what if as age goes higher, there's a lot of variations in terms of the number of children, biological children, because you have longer time to have children. Good. So if you're really young, then there's like really less time. There's really less time to have children biologically, right? So that's why. And if you run an RVP plot, you would have this. You would look at the same, very similar results. RVP plot has. So if you specify RVP plot with certain variable, x variable, it will show the estimated residuals patterns over the specified variable, the predicted, not just the whole predicted value, just the x values, specific x values. Good. So what we do here is that if we control for age at birth or the woman's wage when they had first child, then after that, and then you are expecting that, oh, this must be countering each other in this. So, for example, age at birth, as this variable gets higher, the variability of error terms becomes decreased. Good. So that way, they are countering each other's heteroscedastic patterns. Good. Does that make sense? So that's why you want to control for HF birth to increase the strength of heteroscedasticity. But after you run the regression with HF birth, let's look at our VF plot. Then you still like see some sort of heteroscedasticity going on there, even after you control for So it's not like a perfect method. It's not the perfect method. So that's one way to diagnose heteroscedasticity or correlated errors. And the second way is formal tests. So you run the regression first, and let's look at, is that heteroscedasticity? That's that IID. So the p-value right here is less than 5%, which means that there's some sort of strong heteroscedasticity going on. Okay. It is done. This test is done by you square all the estimated residuals and run an auxiliary regression. On certain predictors, which are most likely the regression of the predictors in the main regression, but this may not necessary. This is not necessary. So does that make sense? So you run the main regression that we're interested in, right? CEB on age of birth, etc., right? And after that, you obtained estimated residuals, right? And you square all of them. Good. And then you run an auxiliary regression of this squared estimated errors on certain predictors that are most likely the regressors in the main regressions. What's the logic behind it? If you use E hat as the y in the auxiliary regression, what would be the coefficients? Exactly 0, right? Because X transpose E is always 0. Oh, X transpose E hat is always 0. Good. The estimated error term and X variables are always linearly uncorrelated. So that way it could be all zeros. But if you square it, and it really represents the variance of error terms, right? And see if any of the coefficients right here is significantly different from 0. Okay. In that case, you have a strong suspicion that there is heteroscedasticity going on. Good. So the gist of this test is to use an auxiliary regression with of the squared estimated errors to test heteroscedasticity. Really have to look at that, but the gist of it is for skewness, you are using E hat to the power of 3, and then for kurtosis, you are using E hat to the power of 4. And there is some revised White's test. This is supposed to be a slightly better one, but anyways. And then as a solution, you are adjusting heteroscedastic or correlated errors by using Euler's estimation with robust standard errors. Okay. So in that case, you're using robust standard errors. So let's look at that. So it's the regression command, all same, but with the robust option. Good. And if you compare the results, okay, if you compare the results between the simple regression model and the regression model with robust standard errors, you would notice that the beta coefficients are exactly the same because it does not do anything with the beta estimate. But the standard errors are now different. Does that make sense? This is all beta coefficients, right? They're all same. Okay? But the second row, standard errors, are now different now that you are using robust standard errors. Oh, what?
What is the third row?
The third one is the T statistic. Good. And that was Eicher-Huber-White-Sandwich standard errors, which assumes uncorrelated error structures. They just adjust for heteroscedastic errors, not correlation among errors. Okay. So the more advanced one, being Zaker standard errors, adjust for clusters or correlated errors as well. So let's say we have some sort of errors shared among women within the same with the same number of children in the household, not necessarily biological children. So they just have same number of children in the household, and then they share some sort of characteristic, and then that makes errors correlate with each other within that quote-unquote cluster. Right? So the errors are correlated among women who have, say, one child, and two children, or one child, two children, three children. They share errors. The errors are correlated within that cluster. Good. So it can be specified by comma, entering comma, cluster children. If it was a SAT score with a school example, the command will be cluster school, right? And then if you look at the results, the standard errors are vastly different for all variables. It really means that the errors are strongly clustered by the number of children in the household. Good. Yeah.
The minimum errors are close to children means errors are strongly correlated within children.
Yeah, within the number of children in the household. Like for women who have one child, they share some sort of errors. The errors are strong.
So, however, the previous hour tests,
Uh-huh.
I think are only for heteroscale tests
Mhm.
rather than like correlated errors.
Right. Yeah. The first robust standard error only covers adjusts for heterogenesis, not for. Yeah. So that means
So how do you know how we are choose some variable and they like
Yeah, it's based on some sort of theoretical suspicions or something like that. So, for example, in the SAT score example, you have a good suspicion that this can be clustered by schools, right? Yeah, based on the theory. And the third robust standard error, which I didn't cover, is Newey West estimator of the BCE or variance covariance matrix of the error term. So it is related to autocorrelation or serial correlation for panel models. I don't think I will have much time to cover that specific part in panel models. But if you have any questions about serial correlation or autocorrelations, you should definitely know because it can be important when you're analyzing a panel model. So on next, in next Thursday's in this Thursday's lecture, actually, we're gonna cover HLM or multi-level models, and then a special case of that is a panel model. So panel model, as long as you're using panel models, then autocorrelations can be a really important issue. So it's a little bit more advanced, but yeah, I don't think this class can cover a lot about it, but if you have any questions or interests, you should definitely. And we have GLS as a solution as well. So let's talk a little bit about the mechanics of GLS. I'm pretty sure you don't really have to know all of this for the exams or the problem sets. And for the GLS problem set, this robust standard errors are like all the things that were covered was robust standard errors, and then there's no GLS questions for data problems. But I'll give you an instruction about it for those who are interested in GLS. Okay. I think it's good to really be informed about GLS for your future endeavor. So I'm just gonna cover it. Okay. So we have this one, this regression model, right? And then the basic intuition behind GLS is that you are weighting people or units. So that way you have IID error matrix. Okay. So first, you are defining this omega or something such that this is So basically, this is the standardized covariance matrix structure for error terms. Okay, and you are defining P such that P transpose P is this one. Oh, inverse. So what it means here is that P is just like a square, right? It is like a square, right? P is the inverse of the square root of the covariance matrix structure, standardized. So again, P is like the inverse of the square root of the covariance matrix. Good. Can be confusing, but.
So the omega is, what is omega?
Omega is the standardized covariance matrix. It's still covariance matrix.
And the sigma.
Sigma is like the shared level, like the shared level of variance of errors, or if it was IID, like so IID means this means exactly I. Right? Does that make sense? Yeah. In the case of IID error structure, omega is exactly the I matrix.
So the sigma and omega, what's the sigma is a matrix and omega?
No, this is a number. Sigma is a number.
What is that?
Oh, the larger sigma is the covariance matrix. Yes.
Correlation matrix or?
Yeah, covariance matrix among errors. That we have seen as with the examples and stuff like that. That we have covered so far. Like we covered this stuff, right? This one. Good. Any questions? Nope. All right. So P here is the inverse of the square root of the covariance matrix structure. Good. And what we're doing here is multiplying P to both sides of the equation. Good. And you define it as mu y, mu x, and mu errors. So that way, variance of the mu e is e multiplied by this one and p e right. And E here and it becomes this one. Good. Oops. Good. So if you don't understand it, that's fine. I can explain that in my office hours. If you don't understand, that's fine. But the logic here the logic here is that if you calculate the variance of E, the new E, and it becomes IID error. Good. So you are multiplying P here, or weighting P. So that way, you have the IID error structure. And then what you're doing here is you are running a regression with the new Y, new X that is weighted. Weighted Y and weighted X. That's what it's doing. Good. Any questions?
So
Yeah.
U E also weighted.
What?
U E is
U-
also is that also weighted E? I mean,
Oh, sorry. What was it?
U the equation of
Uh-huh.
U Y equal U X.
It's not. Oh, it's P.
I don't know, that's
Uh,
Y equal X P plus equation.
this one?
Yes, yes,
Oh, tilde. Tilde Y?
yes.
Oh, okay. Yeah.
Did you say tilde means weighted?
Yeah, yeah. Tilde Y is the weighted one.
And X tilde is also weighted.
Yeah.
And also E tilde is also weighted.
With P. Yeah.
So what's the meaning of like P?
Oh, what? Sorry.
What's the meaning of P, omega, and sigma in this context? We are trying to find these three things.
Uh-huh.
Yeah.
What? Sorry. What was it?
Like what's the meaning of P, omega, and sigma?
P? The meaning of P?
Yeah.
This is, as I said earlier, this is the inverse of the square root of this covariance matrix. Yeah. Because you are inversely weighting the covariance structure. So that way it cancels out the heteroscedasticity and it becomes the IID structure in the new regression. Oh, I'm not sure if I did a good job on this one, actually. I think it should be this one to make sense. Sorry about that. Oops. PE and EP. Right. All right. Then it comes yeah. Yeah. All right. Good. Any questions?
It seems like it doesn't make any difference from the previous equation.
Oh, I changed the transpose and stuff like that a little bit. Yeah. They're same, but then like transpose, the location of the transpose has changed. So it's a really technical thingy, rather than substantive meanings.
I think the result will be the same.
Right, yeah, the results are same. Yeah. I think it's just a better way to present the equation. So, okay. All right, good. So, again, the intuition is multiplying or weighting the inverse of the square root of the covariance structure. So that way, the result in the new regression model, the weighted regression model has an IID sum. Right? Good. But then, to really weight this P, you have to know this covariance structure, right? But then with your one-shot sample, you cannot really know that. So you either have to assume it or estimate. Let's start with the WLS, which assumes the covariance structure. So WLS with the assumption that variance of EI is actually sigma I squared, which is sigma squared WI. So it really assumes that there is no covariance. In this specific scenario, we do not assume that there is no covariance among the errors. And it is specific variance of EI is driven or determined by a certain function of WI. Okay. So in that case, okay. All right. What would it look like?
What is WLS? What's the meaning of WLS?
Oh, wait, sorry.
WLS.
WLS. Oh, weighted least squares estimation. That's when you assume the error structure. So you are assuming that error of EI is dictated by certain function WI. Good. And then without having to say all of this, so in that case, error structure becomes sigma squared multiplied by W1, W2, Wn. Good. Then omega becomes W1, Wn, etc. As a result, omega inverse becomes one divided by W1, 1 divided by W2, etc. Good. And then as a result, P is defined by 1 divided by square root of W1, etc. Dot, 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 dot. 1 divided by square root of Wn. Good. Make sense? All right. You're defining P in that way. And then let's put this 1 divided by square root of Wi as Hx I. So 1 divided by square root of Wi is dictated by Hx, a certain functional form that we are going to assume. Are you okay? Awesome. Good. And in that case, in this, that's the gist of WLS. And so let's look at this practice data set. All right. So this is the new data set, and then with the log price of a house, and the average number of rooms, etc., and the outcome here is the log price of a house, and let's skip all of the formal tests that we have seen from the previous example. And what we're doing here to adjust either scarcity or correlated errors by using the weight option, analytical weight option instead. So you are assuming that. So let's say Hxi here is rooms. So as room size increases, you have a lot of variations in housing prices. Okay, that becomes the error terms, larger error terms. Good, or the larger variance of error terms. And then you are applying the analytical weight of 1 divided by square root, square of rooms. It's room squared. So that way, you can reflect this So you're assuming that the heteroscedasticity is, or the variance of EI varies by the number of rooms, and then you are waiting to adjust for this, the source of heteroscedasticity. Good? Yep. All right. Good. And that's WLS. And the feasible GLS is about the structure of heteroscedasticity being estimated. All right. So so there are multiple ways to estimate the error structure, but one of the ways is to where's the yep. Use this equation. Variance of EI given xi is sigma squared exponentiate this one. Okay. And that way, so you are running this regression. And you calculate the error term, and use it as WI. I mean WI hat, but yeah. And then you multiply this number as a weight, basically. This is a way to deal with heteroscedastic errors. And in this data do file, it actually take a different approach for correlated errors. So the data are looking at state disposable personal income per capita, and I would say data are clustered by each state in the New England region. So it means that data disposable personal income per capita, it has a lot of multiple observations for each state, right? But it has this data for multiple years, across multiple years, right? So you can easily assume that the errors are clustered by each state, right? So what you're doing here is run the regression of disposable income on each year, and after that, and after that, you calculate residuals, right? And then you look at the variance of residuals by each state. So in this robar command, it conducts a Levine's test about a test which is a test for equality of variance across groups, and if it's lower than this p-values are lower than 5%, you can say that equality of variances is not really there across states. Good. So that way you can assume that there's correlated errors going on, clustered by each state. And then you are adjusting that by calculating standard errors of estimated errors by each state, and then use it as a weight, or inversely use it as a weight. Good. That's the whole gist of the FGLS. So if you have any questions about that, let me know, and I'll see you tomorrow in lecture.